Alright, welcome everybody. My name is Engineer Joshua. I'll be taking you through catching technique in computer architecture. Alright, when someone say catching, what is the meaning of catching? It's not something broad, something huge, something new. Alright, it started at the age 80s, our forefathers started it. Alright, when we say catching is a fundamental technique in computer architecture designed to improve system performance by storing copies of frequently accessed data in temporal. Alright, all your access data, they are being stored in the cache, alright, which is the temporal storage, alright, at high speed performances or storage location, which is called cache. Alright, this allows for faster retrieval of that data in subsequent requests, significantly reducing access times and improving overall system efficiency. So here we look at the key points here: high speed, high speed storage between the CPU main memory. I'm talking about this one. Then it stores frequently accessed data, then reduces data access time. It improves system performance, as I stated earlier. Alright, so how catching works. The core idea behind catching revolves around the principle of locality of reference, alright, which states that program tends to access data and instructions that are spatially and temporally close to those they have just accessed. Alright, here's the breakdown: the data request, cache hit, cache miss, cache update. Here's the key point: cache update. After retrieving the data from primary storage, a copy of it typically stored in the cache. Alright, so cache is simply stores frequently accessed data. This prepare the cache for future requests for the same data, uh, hoping to turn subsequent messages into hits. And replacement policy: since the caches have limited capacity, when a cache misses occur and a new data needs to be brought in, an existing piece of data in the cache must be evicted to make room. This might be replacement policy. Example: least recently used, which is the LRU, and the least frequently used, which is the LFU, and the FIFO, so on and so forth. Alright, so someone asked why caching is important. It avoids repeated memory access, increase CPU efficiency, save times during program execution, and essential for modern processes. Alright, let's move straight to the types of cache. We have the L1, L2, L3, and the disk, which is last but not the least. Alright, CPU caches. These are the fastest and closest caches to the CPU. So the L1, L2, L3, and the disk cache. These are the fastest and the closest caches to the CPU. The L1 is the fastest built in the CPU, often service into instruction cache. L1 data cache integrated directly into the CPU core. The L2 cache, alright, larger than the L1 but slightly slower, can be on chip or near the CPU. Alright, see, larger, slider, slower, supports L1. The L3 cache stores among CPU stores. Shared among CPU cores, which is the largest and the slowest of the CPU caches, often shared across multiple CPU cores. It acts as a victim cache for L1 and L2 misses. Keep it in mind in case you came across it anywhere. Alright, after the lesson, I'll be dropping some slides so that you'll be going through. Alright, so you'll be going to the caching techniques: the direct mapping, the associative mapping, the set associative mapping, and the last one, which is the right through, right back, but not the least one. Alright, so first of all, I'll be talking about direct mapping. Each block maps to one specific cache line. Associative mapping, I will not spend much time here. because we need to run faster so that we catch up our lesson. Alright, so block can go on anywhere in the cage, which is associative mapping, set associative mapping, combination of direct and associative. Okay, the last one is the place I'll be hitting most: write through, write back technique. Right, when we say write through, the data is written simultaneously to both the cache and the main memory. This ensures data consistency but can be slower due to main memory write overhead. Or when we say write back or write behind, data is initially written only to the cache. It is written to main memory later, typically when the cache block is affected or when the system explicitly flashes the cache. This is faster for writes but requires more complex cache coherence mechanism to ensure data consistency, especially in the multi-processor. Keep in mind, in a multi-processor. Alright, let's move straight to the cache mapping techniques. The direct mapping is simple, very simple and fast. One memory block maps to one line. Right, that's why we say one-to-one faction. One memory block maps to one line, only one line. Keep in mind, right? The fully associative mapping, any block can go anywhere. Yeah, this is mainly to one. Yeah, keep in mind so that you remember yourself. Alright, the flexible but slower set. Alright, flexible but slower set. Then let's go to the set associative mapping. Caches drive into set. Block maps to any line within the set. Alright, so let's move straight to the advantages and limitations. Alright, when we talk about advantages, here are the important or the crucial benefit we get from cache. Alright, so a faster access frequently used data, reduces average memory access time, it improves the CPU, which is the central processing unit performances. When we talk about limitation, it's limit the cache size, and also not effective for non-repetitive data source. Keep in mind, not effective for non-repetitive data source. Alright, so summary: at the end of this lesson, you should explain what caching is, caching techniques, and all those things. Alright, summary: caching stores frequently accessed data closer to the CPU for easier retrieve, or for in case you need it in a short period of time. It occurs at various levels within the computer system, each with its own characteristics and purpose. Here, better user experience for faster loading times and responsiveness leads to more fluid and satisfying user experience. Alright, so the cache stores frequently data that designed to improve system performance. Frequently access data to improve high speed average location. Alright, so type L1, L2, L3, each has its own speed and size, uses temporal and locality principles. It improves speed but has and complete trade-off. Alright, so let's talk about it. Conclusion. Alright, caching is a sophistical and essential techniques across all levels of computing for the smallest CPU register to global content delivery network, playing a vital role in a modern system performance. But first of all, you need to keep in mind that caching works behind resolve around the principle of locality of references, which states that program tend to access data and instructions that are spatially and temporally close to they have just accessed. Alright, so I'll be urging you to take your study serious. See you in the next video. Thank you.